Hello, this is Instructor Rick Powers, Western Technical College, Basic Statistics. Lesson 25, Confidence Intervals, Proportion. When we want to make a confidence interval for a proportion, it's important to know what that really means. We start with sample information, and we get an interval which, we hope, will contain population information. For example, we might have a group of 200 patients that are being treated for migraines, and 10% of them experienced weakened muscle tone. So we want to know, based on that sample number, what would be the population proportion. We know the population number may not be 10% because of sampling variation. So we want a method that will give us an interval that we can trust to be somewhat accurate so we can have some confidence in it. Major idea, you need to learn to use technology to find the answers. The textbook and the homework examples might take you through using formulas, but that is not as important as getting the technology to work for you. It's faster, easier, more accurate once you get used to it. Let's do the example. Sample size of 200, sample proportion of 10%. Find the 95% confidence interval for the proportion. Answer, 5.8% is less than P, which is less than 14.2%. Meaning, the population proportion should be between 5.8% and 14.2% with 95% confidence. There are things to learn from the equation, so here they are. The lower bound, P hat minus Z sub alpha over 2 times the square root of P hat times 1 minus P hat divided by N. Upper bound, same thing, but with a plus sign instead of a minus sign. Note, it must be the case that N times P times 1 minus P is greater than or equal to 10, and that the sample size is less than 5% of the population size to construct this interval. First, note that the form of these equations is like the empirical rule, a center number plus or minus something times the standard deviation. Second, note that we can only use P hat, the sample proportion in the equations, because we don't know what the population proportion actually is. So right away, we are guessing that our value is pretty close to the population number. Note that the width of the interval is affected by the sample size. As mentioned previously, if we have a larger sample, then the results will be more accurate and the width will be smaller. Many people wonder what is going on with the z-score. The z-score is being used to adjust the width of the interval based on the amount of confidence that we need. Since we know the sample distribution is bell-shaped, then we can use the z-score to make sure our interval has a chance of hitting the target. If we have an interval that is as wide as 95% of the sample data, then it has a 95% chance of hitting the target. We label the z-score with the area of one tail. Note, if the confidence level is in the interval, then alpha is in the tails. So alpha has to be divided by 2. So the z-score has a label on it of alpha over 2. We do not divide the z-score by 2. The label is divided by 2. Consider the example. If we have 95% confidence, then alpha is 0.05. We want 95% of the data in the middle, so we split alpha into 2 tails. The z-score is labeled as being z of alpha over 2, 0.05 divided by 2, or z sub 0.025, which is 1.96. So what happens if we try to be more confident about the result? A large confidence interval will contain more possible data. So then alpha will be smaller, the tail is smaller, the z-score is larger, and the interval is larger. More confidence causes less accuracy. Example, how much will lunch cost at a restaurant? If I say between $0 and $100, well, that is correct, but it's not very accurate. If I say between $4.50 and $4.75, well, that looks more accurate, but it has less chance of being correct. By using these mathematical tools, we hope to balance our confidence and our accuracy. We want to have results that we can trust and results that give us good information about what to expect for population measurement. End of lesson 25.